Okay, so welcome back to the afternoon session. Our speaker now is Aditi Raghunathan. She's a postdoc here at Berkeley and moving soon to CMU. And she will talk about understanding the robustness of deep learning.
All right. Hi, everyone. I'm Aditi, and thanks to the organizers for inviting me. So I'm quite literally, by the definition, moving to CMU. So if there's anything that doesn't make sense in the slides or what I say, it's all because of the fact that I'm moving. Okay, so when we think about robustness, it's like a question that a lot of people are thinking about these days. And the typical story that we have in mind is, when we are thinking about using ML in safety critical applications like self-driving cars, it's very promising, but like sometimes we find issues happen. For example, in this incident, a woman was killed because, among other issues, we didn't recognize, or the model didn't recognize a pedestrian who was jaywalking because it was only trained on pedestrians at crosswalks. And then maybe an example that hits closer to home now is that you want to train on certain weather conditions, but you want it to work all the time, especially in unpredictable weather and so on. So this is the usual, So this is the usual story when you think about robustness. And of course, this is really important when we think about deploying systems in real world applications. But in this talk, I kind of wanted to say why I think robustness is interesting and shed some important perspectives on machine learning more generally. And so this is very hand wavy, but this is kind of the way I think about it. What dictates a model's predictions? So at the end of the day, there are two components that kind of come together. One is the training data that you give the model, and then there's this, inductive bias, or like the rest of the stuff, which is basically your architecture, how you initialize the network, what does gradient descent do, and so on, which says how this training data actually is used to make the predictions. And we need to think about both of these together usually. But I think robustness, which basically looks at the performance on a different distribution as the training distribution, could actually be quite interesting because, by the nature of robustness, you're kind of reducing the effect of training data on the model's predictions. And you can really see a little bit more of what the inductive bias or this nurture component is, because if you look at predictions outside or like very close to the training data, all models might really be doing the same. But by really looking things outside, you're stress testing and seeing like, what exactly is this nurture or the inductive bias component. Oh no, I switched the two. What's the nature of this component? And this one, I'll try to like share some of these observations and perspectives, in this talk. I had the I could look at the rest of the program because my talk was TBD till very late. And so I saw that most of the talks were on supervised learning. So I thought it might be interesting to talk about a setting that is gaining quite some prominence lately on transfer learning or pre-training or, foundation models or whatever. So I'll talk a little bit about that first, and then in the end mention various results on supervised learning, roughly along the same format of seeing what interesting things can we learn about how these models learn when we actually examine the robustness or the performance of these models outside this IID setting. And the way I'll try to organize in each of these settings, the kind of results is, so we'll start with some empirical observations about how these models perform in practice. And typically we'll try to find something that's interesting or, that's a little bit unintuitive and try to capture that in a theory setting. And the hope is that by writing down some math and actually being able to prove something in a stylized setting, we actually gain some intuition or understanding of what is going on or what captures some of these empirical observations. And really the gold standard would be that we use this theory or the insight to come up with some useful solution. Now, because we are in a stylized setting, we should be able to manipulate things and move them around and like get a solution that makes sense. And again, like really it'll be cool if we can translate this theory solution into something in practice as well. This is kind of what we'll hope to do, or like what I hope to do in most of the projects, and I'll try to keep this outline for the talk as well. So the idea is that this theory setting captures some intuition or understanding, and like we can actually test this intuition or understanding by seeing whether we can change the training method or like something in a way that actually fixes or shows empirical observations that would be predicted by our theory. So with that, I'll jump right into the first part of the talk on transfer learning and robustness. So here's the general pre-training setup. And this is a figure that I've adapted from Bomasani et al. So the idea in pre-training is that you have like multiple steps in the process. So in the first step, you do this, what is called pre-training, where you collect a lot of diverse data from the wild. And so you don't think too carefully on what exactly this data is or how it's related to the final task. You just collect diverse data from the wild and do kind of a pre-training and use that to get something called a pre-trained model. And once we have this pre-trained model, now we do our usual machine learning setting of where we have some training data that is relevant to the task we care about. And then we adapt this pre-trained model on this training data. And you could do multiple tasks. And so depending on which task or which distribution you are in, you collect appropriate training data and you specialize this pre-training model to that narrow distribution. So in a supervised learning, you would typically only do step 2 and you'll start with a random initialization. But instead here, what we're doing is we're starting with this pre-trained initialization and then using the training data that is specific to the task we care about and trying to adapt this model to work well on whichever task we choose to. Okay, so why should we think about pre-training? And one example that I think is pretty compelling is, say we want to do satellite remote sensing. So the idea is that we have satellite images of different regions and we want to use that to tell us what is happening in that region. And that's a way to assess what is the development happening in different places. But the challenge here is that we typically only have training data from certain regions, which is like typically we get more annotators, we have more information about what's going on. And that's kind of not the point of the task. Like actually, when we want to use ML is the case where now we want to generalize to a setting where we don't have as much data, for example, in Africa. So now if we just do the typical machine learning, the supervised learning, what you do is you'd start with a random model initialization, and then you would train it on this in-distribution training data, which is North America. And unfortunately, because models are typically not robust, they don't do very well on this new distribution Africa that is slightly far from this training data of North America. And so the whole reason we wanted to do this in the first place, which is of like, using ML in places where we don't have annotation, kind of doesn't really work. But maybe this is like not that unexpected because, well, the model has never seen any data from Africa, has no information of what to do. So maybe we shouldn't expect this to work. And so the idea in pre-training is that now let's actually train on diverse data. Like it need not be annotated, it could be unlabeled, but like in the process of hopefully given data from a lot of different geographic locations. So at least the model has some notion of like what data from Africa looks like, but not with explicit annotations. There is some information here. And now let's try to retain that information and then add on like explicit annotation in the task that we care about. And what we find is actually it is true that doing some kind of pre-training does enable better performance on out of distribution settings like Africa here, because the fact that you've trained on such diverse things in the beginning enables the model to actually generalize better to a distribution that's unseen in this particular adaptation stage. So especially for someone like me who works on robustness, I think I find pre-training quite interesting because it really is one of the most promising ways to actually improve robustness. Yeah, I guess just to summarize, yeah.
Sorry, so in the first stage, when you don't even have supervised data, what is being fitted? So what is pre-training?
Okay, I should have had a slide on that, but okay, the usual, you try to create different ways of utilizing the data. So one thing is just do a generative process. So like try to generate the data itself. So you could learn a generative model that generates the kind of data that you see. And so this model typically will like do it in a way that actually incorporates structured information about these data sets. So for example, if you look at images, you don't need to know exactly what the task is, but there are certain things of the image that are important, like what's the object, what's the shape, like what kind of backgrounds is it typically found in. For example, if it's a bottle, it has a particular shape and all of that. So that information can actually be distilled even without labels because it sees a lot of data.
Reduction.
You could think of it as a dimensionality reduction. There are other ways that people do pre-training, which is, you can incorporate one thing that's called contrastive learning, which is you like, for example, that certain like rotations preserve the object, but or like cropping preserves. So you learn a representation that is invariant to like cropping or rotation on this unlabeled data. And somehow this representation, like dimensionality reduction is better. The other thing you could do is like mask out certain parts of the image and try to regenerate it, which is kind of like denoising autoencoders. So you can regularize it in a certain way that actually enables it to capture the right information in the representations. And because of that, like maybe if you've trained on data from North America and Africa, it kind of disentangles it in a way that captures some structure that is more general than if you're only trained on data from North America. So that's the goal. But again, all of this is informal and we have no sense of proof or theory that any of this is like actually happening. Any other questions? Okay. So just to summarize, so like, like I said, like vaguely, you could think that pre-training incorporates some information that is potentially more diverse than what just happens if you had a narrow label set. And this is typically improves in distribution performance, but it substantially improves out of distribution performance. And it's probably one of the most reliable methods that we have to date to improve robustness across several natural shifts. So in some way, it's not great because all it's saying is that you train on more data, it works better, but on like robustness, but it's kind of the only thing that actually works when you don't have any, when you have these natural shifts that you don't really know what's happening. Okay. So given that it makes sense to use this notion of pre-training, that is of being able to train on diverse unlabeled data, how do we actually use pre-trained models? And that's kind of going to be the focus of this talk. So how do we leverage this information that's contained in pre-trained models? So first I'll discuss two popular methods, and then we'll use that as a way to think about what we should be doing. So one idea is what people typically call fine-tuning, which is you start with this initialization, and then you have, so for example, you could have like features. Now you add a linear head that looks at these features and gives a label. And then now you backpropagate, you randomly initialize a linear head, you initialize the rest of the model to be what pre-training gave you. And then you do a few gradient updates on this in distribution training data with like cross entropy loss. So that's the usual fine tuning, which is basically you've replaced a random initialization with this pre-trained initialization, and you run a few steps of gradient descent rather than running many steps so that you don't lose all this information. So that's one method of fine tuning. And the other method is that, maybe we shouldn't change these representations at all. And especially people think of this as a way to do cheaper fine tuning. So you don't even change these models. You don't have to store them in memory and pass gradients and all that. You just use these representations on its own, keep these fixed, and just learn the linear head. And that's called linear probing. So these are like two most popular methods of using pre-trained models that are considered in literature. One of them updates everything. One of them updates only the linear head. And this is typically known to be more memory efficient, but the other one is supposed to work better. Okay. So what is the challenge in trying to think about what is the right way to fine tune or use these models? Because there are really several moving pieces in addition to what we're usually used to. So usually we have just the model architecture and your one training distribution. But now you have to think about the pre-training distribution, the pre-training loss or the procedure. And then we need to think of this downstream or adaptation distribution, and also like what is the procedure. So there are all of these things that now all interact together in deciding what's your final performance. So for the purposes of this talk, we'll like not worry about these four components and really only focus on this adaptation procedure. For example, like linear probing and fine tuning are two different adaptation procedures. And so we'll think about what is the right adaptation procedure we should be using. Okay, so I'll start off with some empirical observations. So I know we all just got back from lunch, so this is going to try to be a little interactive in this part. So just to summarize again, so we are comparing two procedures. One is fine tuning where everything is propagated, and linear probing where everything is fixed except the linear head. Okay, so let's look at this data set breeds, which is a quite an interesting data set for studying robustness. So the task is to classify into animal categories, and we create they create a distribution shift in the following way. So there's one subset of ImageNet hierarchy, and so you like take the root, and then you have two subtrees. So one of them is train and one of them is test. So they're all the same animal, but like different subtypes of that animal, and that's how you split these data set. And the pre-trained model we're using is MoCo V2, which has seen unlabeled ImageNet images. So it has seen all these images. So it has seen unlabeled versions of the train and test. And so that's the pre-trained model we'll be using. And so we want to see which method does what here. So by show of hands, do you think if we look at, okay, so these are the in-distribution performances. So just to get everyone on the same page, if you train from scratch, you get 92. But if you did this pre-training, you already see some boosts because you've trained on more diverse data, which has kind of, that helps. And so linear probing gets some amount, and then fine tuning further improves the performance because you're training all the parameters and not really just a few parameters. So this is what in-distribution performance looks like. So now let's try to see what happens out of distribution. So on Scratch gives 58%. So there's obviously a drop, which is what we're typically used to when we think about robustness. So do you think linear probing that allowed us to start from a pre-trained model would actually improve performance over Scratch out of distribution as well, or not? So by show of hands, how many people think that linear probing would do better out of distribution? I guess most people. Okay, and you got it right. Yes, it does better. So you see there's actually quite a bit of boost just because you've used pre-trained models that has seen this diverse unlabeled data. So now let's look at the other rules. So do you think linear probing does better than fine-tuning out of distribution? So notice that in distribution, linear probing did worse than fine-tuning. So what do you think is going to happen out of distribution? So how many people think linear probing would do better than fine-tuning out of distribution? Show of hands. Okay, so most people think so. And oh no, this is wrong. My slides are wrong. Yeah, like I said, I knew there were going to be some typos. So okay, so yes, you got it right. So yes, it does. So surprisingly, the linear probing does worse in distribution, but it does better out of distribution. And this is actually kind of surprising because if you look at the literature on natural robustness these days, there's a little bit of a narrative that improving performance in distribution improves performance out of distribution as well. But here we see there's actually a bit of a flip, that something that we typically do without thinking, which is fine tuning, it seems to be typically better, but it does actually worse out of distribution. Okay, so let's look at another data set now. Oops. So let's look at another data set. So this is CFAR 10.1. And the task is to most people have probably worked with CFAR 10. There are 10 categories and we want to classify images. And so this test distribution, which is the out of distribution, is like a near replication of the pipeline done by Recht et al. And so they just collected a new CFAR 10 data set with the same protocol, but using different unlabeled images to start with. And again, the pre-trained model is now ImageNet, which is a much larger data set. So by pre-training, you're seeing a much larger amount of data than just the original CFAR 10. So we'll repeat the quiz, and I'm also like, oh, what's going to happen on my slides? So yeah, so what do you think is going to? So okay, I removed from Scratch because it's quite clear it does better than Scratch, both linear probing and fine tuning. But let's go back to linear probing versus fine tuning. So how many people think that in this data set, linear probing does better than fine tuning over D? Few people. Okay. And the answer is no. Yeah, I got it right. So the answer is no. So here, surprisingly, for this data set, like fine tuning does still better. And so what is different is that in this data set, the distribution shift is really small because they've really tried to keep the distributions close. And like there are some differences in how it was collected. But in general, the test distribution CFAR 10.1 is much closer to CFAR 10 than in the previous breed setting where you actually like had different subcategories. And so in that case, linear probing actually did better out of distribution. But here we find that actually fine tuning does better. Yeah. Oh, sorry. Thanks. Yeah.
How does this compare to, for example, training like the last linear layer as well as the last convolutional layer? Because I think that's like supposedly like people think that maybe that combines the best of both worlds.
Yeah, so at the end of the talk, we'll talk about combining best of both, but the particular method that you said, if I remember correctly, we tried it on a few data sets, like we varied the number of layers that are trained and typically interpolates in performance between linear probing and fine tuning. So if you're in this situation, then it will do better than linear probing, but not as good as fine tuning. And in the previous case, it will do better than fine tuning, but not as good as linear probing. Yeah.
Both data sets, what happens if you train the strength on distribution and test on distribution?
I don't have numbers, but they would be in the high 90s. Like people have tried that, and like if there is no distribution mismatch, like they do just as well. So maybe CFAR 10.1, I think that it might be slightly harder than CFAR 10, so accuracy is a little lower for the same amount of data, but in like the breeds case, like you get the same performance as training in distribution. So if there is no shift, then performance is quite good. So it's not like the task is inherently harder, if that's what you're asking.
Yeah, and what's the random prediction like baseline? 50%?
10%, so like 10 categories.
Okay.
Okay. So to summarize, so in this small game, what we found is that it's like a very it's not clear which method does better, but when you look at an average over 10 data sets, what we find is the common wisdom is that we should do fine tuning if you can, and people typically only reserve linear probing if they're memory constrained. But actually we find that in distribution, yes, that is the case, but out of distribution, the story is more nuanced, and at least across these 10 distributions, we found the reverse trend. So yeah, I think on 8 of the 10 data sets, actually linear probing performed better. And on a few data sets like the CIFAR 10.1 example, it didn't do. Yeah.
I wonder, did you try to restrict how far away you can go in fine tuning from the point from which you fine tune,
yes,
or using small learning rate shadow, or using some clipping of the gradients or something?
Yeah, so one thing that you could do is like doing a L2 regularization towards the initial initialization or something. So people have tried things like that, and it does improve over fine tuning a little bit, but not as much as linear probing.
But did you check also your results, how far away your final weights from the initial when you start to do fine tuning?
So we'll get into that a little bit, like we did, yeah. So we'll talk about how to get the best of both, and how does it compare and stuff. Yeah. Okay. So hopefully this lecture got people interesting to think. So I think I remember that given the trend that these big companies are releasing big models, and like what should we do as students and all of that. So hopefully this at least tells people that it's still pretty non-trivial and unclear, like how do we use these models, and hopefully there's still interesting research and stuff that has to be figured out. Yeah.
Could you explain again what the
yeah, I think I have it on the slide. Yeah. So in fine tuning, you start with the initialization where you change all parameters and your gradient updates. But in linear probing, you keep your features fixed. That is like your last but one layer is fixed, and you only train a linear layer on top. Like you only adapt that linear layer on your test distribution, like whatever, like adaptation distribution. So here, like some parameters are fixed, whereas here all parameters can change. But they all usually change. I mean, you don't train for like as many steps as you typically do. So it's still better than doing from scratch, even if you do fine tuning. Oh yeah.
So I guess about your empirical finding, does it matter like in some regime where you're doing these experiments? Like, are they like in an overparameterized regime where you have like more like parameters and samples? Perhaps you find the opposite thing if you operate in a different regime, or
yes,
maybe more samples.
Yes. So as you increase the number of samples you have during adaptation, the effect does go down. Yeah, so it is important that we are in like a setting of like limited data. So in fact, you don't even have to do out of distribution, just in distribution itself, you will see a similar effect if you restrict your samples enough. So if you like take CIFAR 10, but just take like say 500 or 1,000 examples, you'll still do somewhat okay because of the pre-training, but then you'll see that actually like linear probing would do better than fine tuning, even out just normal IIT as well. So, but it is important that you're in a regime you have more parameters than data. Yeah. And we'll see that in the theory as well. Okay, cool. So this is just to quickly summarize. So this common wisdom, we might want to question, especially out of distribution. And of course, this is not always. It typically happens when you have high quality pre-trained features. So if your features are not very good, linear probing probably can't do very well, to start with. And we actually saw this. So in MoCo V1 versus V2, we see that in MoCo V1, which is worse, linear probing doesn't do better than fine tuning. But when we use the better pre-trained model, linear probing does better than fine tuning. And of course, larger distribution shifts, like, in the extreme where test and train are the same, then fine tuning does well. But as the shift becomes larger, like there's a tendency for linear probing to do better. And so this kind of, inspired us to think really about like, how do we improve this downstream performance? At the very least, we should be able to get the best of both because that information is contained in the model. Okay, so now we'll talk about the theory setting. So, transfer learning is not new. People have tried to study transfer learning in the past, but most of the work on transfer learning only looks at linear probing, which happens to be a convex problem. And in this work, we really want to think at least about fine tuning and linear probing. So we need to think about this fine tuning, which now makes things non-convex because all these parameters are changing and they all interact with each other, getting a non-convex objective. This is one typical challenge that we again have to revisit when we think about how do we analyze this finding. And the other thing is, it is the same objective as training from scratch. So we still want to also capture that fine tuning does better than training from scratch. So just looking at the usual objective is not enough. And we need to really think about the training dynamics that was starting from pre-training. So we can't do, for example, like the NTK kind of relaxations, assuming random initialization or something like that, because we really want to also capture that we are in the pre-training setting. So I think this is a pretty interesting regime for theory analysis in general. And so hopefully more people are also excited about like, how do we capture these analyses? And in this talk and in this work, we do something pretty simple, but like already gives us something interesting. Okay, so here's the brief intuition for the theory result. So let's say this is what the features look like. So you have blue in ID and green in OOD. So this is like a toy. This is not any real thing. It's just an illustration. So let's say that the features were good such that you do end up separating the crosses and circles roughly in a direction the same for ID and OOD. But of course, the domains are also somewhat separated because they are ultimately different data points. And without labels, there's no reason that it was collapsed. So let's assume this is what like a good features look like. Now, what happens when we do fine tuning? So we first initialize a classifier, right? So this could be this initial head. And the crucial thing here is that when we're doing fine tuning, we're changing all parameters. So we're going to change the features as well as the linear head together. So suppose we have this as the initial head. Now, when we take a gradient step, we're going to change the features. So to simplify, let's assume we're doing like alternations. So let's see how the features change to accommodate this head. The features will change that way, and now the head also will change. And so basically, both of them are going to keep changing. And because of that, the features change, Because of that, the features are going to change in a way to accommodate the head while the head also changes. But in a simplistic case, let's assume that the features are separate enough that your OOD examples now, because they were not trained on, there's no reason for these features to change much. So these features don't change. As a result, what has happened is that the head, which was obtained for this data set, doesn't work as well out of distribution, because here the features have changed and the head matches those changed features, whereas OOD, nothing has changed. And now like whatever information was initially captured in the pre-trained information is kind of lost in the process. Does that like kind of intuition make sense? Yeah. So that's just because I guess a little bit of the overparameterized setting. So like if we found this, I mean, we tested this empirically as well, but this is just like an intuition that let's assume they're in a different subspace as the training data. And so like you're not basically never like updating anything to do with that representation. Sorry?
In this setting, you assume the factorial weights are something.
No, nothing is frozen here. So you assume the features can change, but you're assuming in this, we are in this overparameterized setting where there are no gradients related to the points OOD because your training loss doesn't have anything to do with these dimensions. It only has like a few dimensions, which is corresponding to your distribution. This is a little hand wavy, but you can think of this as the OOD examples lie in a different subspace as your training data with respect to the features. So the features are not going to get any gradients. Yeah. Yeah, the margin doesn't matter. The reason we have this small margin is because, I'll get to that, but it's about linear probing. So at the end of the day, it's not like your features are going to be great because they're trained without any annotation or like diverse data. So it's not like the features are going to be great. So it's probably something like this, which is why linear probing doesn't work well. So yeah, so we assume low margin just to replicate the case where linear probing doesn't work as well. So your features are not perfect. So the data might not be separable in the features, but yeah.
So by only here, you mean that you only train on the data that
Yeah, so basically if your data is far enough out of distribution, so for example, in like the breeds, like you have all these different subpopulations and they're going to be in different parts of the representation. So you're never going to get any gradients with respect to those parts that are not in your training data when you just update on the training loss.
So then how can you still be beneficial compared with?
Yeah, that's a good question. So here it's like obviously stylized where things are like totally disrupted. So maybe you won't do as many gradient updates. So it will not change this much. So like, maybe it'll be some, like in practice, you won't run too many gradient steps. So it's not going to be totally corrupted. So you still have it might be something like So this is a bad illustration, but like basically here is like trying to be too extreme, but you can imagine that if you run like a few gradient steps, your features do change a little bit, but it still has more structure than if your features were randomly initialized. Because you're not like totally overfitting to, you're starting from a representation that is capturing some semantic and you change only a few times or a little bit. Yeah. If you run it forever, then like, the similarity is going to be lost and you'll probably get back to the training from scratch kind of a situation, but you typically run it for much fewer steps. So it's implicitly regularized.
So from training,
Yeah, if you run it like for a long time, you end up overfitting anyways, and you lose information that you have. Yeah. So typically you do have to early stop if you want to keep gains.
Yeah. So how do you decide when to stop?
Usually people have a validation set. So here, like any validation that we have done in any of the experiments was just in distribution. So, and like what linear probing could, or why it could be doing better is that like here you're not changing the features at all. And so you like would end up learning a linear head that looks like this. And so this would do better out of distribution because the head is still decent on these examples. But like, one of you asked, you do end up, because the features are not perfect and you're only learning a linear classifier, if your features were not linearly separable to begin with, there's not much that you could do. So you might end up doing worse in distribution, which is kind of what we see in practice, which is why typically we do fine tuning because the features are not perfect. But in the process, we might, affect the robust. Okay. So this is a summary, like this idea of feature distortion is that fine tuning can lead to the feature distortion. And why that is because features for in distribution is when you're doing updates on, there the features will change in sync with this linear head that you're trying to learn. And if your random linear head is initialized very far, then your features might also end up changing a lot to accommodate this linear head. And OD, the features change a little less or much less because they're not trained on. And we did check this empirically. So the ID examples, like if you look at the representations and see the L2 distance, they change by an order of magnitude larger than the change OD. So it is true that you could roughly think of in this overparameterized setting that the OD is like kind of unseen directions that you don't get really gradients on when you do this adaptation. And the result of this is that this head can fit can fit distorted features. That is totally fine if you only care about in distribution performance, because together as a unit, they're still okay. But in the process, you've started performing worse on OD examples that originally they were more semantically related through the features, but now you lost that structure because of distorting features. So this kind of captures what we saw in practice of why linear probing does better out of distribution despite doing worse in distribution. So to kind of prove something about this, we considered the simplest setting that we could try to replicate this result in. So we have two-layer linear networks. So here's a figure. So you have inputs and you have a linear feature extractor, and then you have another linear head. So this is just to make analysis easy. And so your ground truth is the product of these two. So things are still non-convex, but it just doesn't have the non-linearity in the activations. And we use the square laws. Again, it makes life easier. And so we want to train models and evaluate them on the squared laws. And just to recap, in fine tuning, we update both these parameters, this head and the feature extractor. Whereas in linear probing, V is like fixed at whatever you get after pre-training, and only the head V is updated. So if we were to contrast linear probing and fine tuning, we need at least two layers for that reason, because there are two sets of parameters. And this is kind of the most simplest setting we can study. And in both cases, this linear head, again, in practice as well, what is done is it's randomly initialized. So V is randomly initialized, B is initialized at a pre-training. So the assumptions that we make are that your pre-training is good. And so if you recall, we really see this difference only when the pre-trained features are good, and empirically we saw that too. So we are in a setting where we can actually bound how close B naught is to the B star, which is the optimal ground truth. And up to rotations, we measure how far they are, and that's this quantity epsilon. So in this work, we assume that epsilon is small and we can bound by epsilon how far your pre-trained initialization is. And then the other simplifying assumption we make, which is kind of common in transfer learning, is that B0 and B star have orthonormal rows. So I don't think this, like, we could massage things to work even otherwise, but this doesn't change the intuition much, but makes calculations easy. And the other thing we do is we assume infinitesimally small learning rate, so we can analyze the gradient flow equations. So those are the assumptions. Like basically, the most important thing is that we are close and we make the gradient flow assumption. So what does the data distribution look like? So this kind of answers some of the questions that came up. So we didn't want to make any distributional assumptions, so we just made it as simple as we could think of, which is that we have a span of training examples. So we have n training examples, and so S is the span. So I don't remember if I mentioned before, but K is the dimensionality of the features. So we are in this overparameterized setting where n is, or the dimensionality of S is less than D minus K. So what this really means is that there has to be this notion of something that is unseen in your adaptation process. So if your adaptation basically gave you information about all parts of the features that matter, then we don't see this effect. Fine tuning is still fine. But we want to really be in the setting where the representation has more parameters than the training data. So there are some unseen distributions or tests. And that's basically how we define the test. So we define test to be something that has an invertible covariance, which means that the test distribution or OOD measures all directions, even though the training only had a few directions. And this kind of crucially captures that we care about adapting in a way that all directions are preserved and not just the training directions. And again, we measure OOD by the same squared error. And yeah, we make this assumption OD that things are invertible just to say that we want to find the worst case directions which could have been distorted. And we assume that your training regime is such that you have fewer samples than parameters. So yeah, we are in this setting where there are directions not seen. Like again, like most things that I've seen in robustness, actually, they don't happen in the underparameterized setting. So if you had fewer data points, then you will never really, fewer dimensions and data points. It's really hard to construct a setting where one method does better in distribution, but does worse out of distribution, unless there's a lot of noise in your training data. But in the overparameterized setting, you actually find these happen quite often. So what we prove in this paper, which I'm presenting a very simplified version here, is we can lower bound the OOD error of fine tuning. So we can say that because of this feature distortion that happens, we can prove that the OOD error can never be much lower because the OOD measures all directions, whereas your training data had only a few directions. So let me unpack these quantities. So we have this alpha by K part. So alpha basically measures what is the interaction or the angle between what is missing in the training data and this, or like the features that you have. So if your training data is missing a lot of important parts that actually affect the features, if alpha is larger, then we find that this lower bound increases. So this intuitively makes sense that if your rows, so basically B0 already projects out some parts because it's a dimensionality reduction, but we say that if B0 doesn't, but if, in your training data, you still have directions that B0 hasn't projected out that are important, but you don't see it in the training data, then you have this kind of interaction that causes issues. So alpha is the principal angle that it's like a generalization of the cosine angle. And we find that that is a quantity that determines the lower bound on the OOD performance. So the more B0 interacts with missing directions, the larger the OOD error can get. For the same reason that we saw earlier, because of the random initialization of the head, the two can interact and change unseen directions in a way that could be quite bad.
Previous slides, what you were mentioning was this B, which is like a pre-trained feature, uses both in distribution and out of distribution data. Mm-hmm. So over here, you're saying that it doesn't see out of distribution data.
Yes.
But in the previous case, it was.
Yes. So pre-training sees out of distribution data, which is why your B0 is close to B star in all directions. So if you look at the assumption here, so B0 is close to B star in all directions. So the L2 norm is small. So they are close in every direction because B0, which is what is obtained after pre-training, has seen everything. So it gets all directions close. But now the question is, can we preserve these directions of B0 when we do fine tuning or not? And so in the fine-tuning process, in the adaptation process, you don't see everything. So you have limited data for which you have labels on, but you're still updating all parameters. So that's precisely why that quantity comes up here, which is, B naught was close to B star in all directions before. But then now if you're going to change that or mess that up because there are directions that were unseen, but you still make updates on through the head, then you have this problem. Yeah.
So K is the number of missing directions in
K is the dimensionality of the representation.
Of which representation?
Of the B naught.
Okay.
Yeah, so alpha by K is basically the fraction of missing directions. Yeah. Yeah, S perpendicular, sorry, I don't have it here. So S is the span of the training data, and S perpendicular is basically the orthogonal, what is missing in the training data. So there's a lot of important directions. So all of B naught could be important because your OOD has all directions. So if there's a lot of B naught that is actually missing, then you are in danger because your features could be distorted in a way that actually affects your performance.
So it's B naught and B star.
Yes. You could think for purposes of this talk, you just assume B naught is B star. So let's say you have perfect features. So B naught is B star, but you might mess up these perfect features by doing gradient updates. And the amount you mess up depends on, so you will not mess up in directions that you are getting data on because you assume the data is good and not noisy, but you could mess up on unseen directions. And that is what this S perpendicular measures. So the more unseen things interact with B naught, the more your OOD error could increase.
Could you do fine tuning while enforcing that the features are still good on the?
Yeah. So that's kind of what we'll get to in a bit. Yeah.
Sorry, I did have a question. A priori, making it so the outer distribution data has more missing directions doesn't actually make things worse. It's if it's having more fraction of the directions being missing, kind of
Yeah. It's like the fraction that matters. Yeah. And then the other interesting component is actually what we'll use for fixing this. So we can't change this fraction much because we are given the training data and we are given B naught, we're given the pre-trained model. But this other quantity is actually interesting. So this quantity, so it has this slightly complicated form maybe, but intuitively, it measures the alignment error. So V star is your perfect head. So recall that the ground truth is V star and B star. So V star is the ground truth perfect head, and V naught is what you initialize. So phi over here measures how far V naught is from V star. So if you initialize V star perfectly, and let's say we did one update, B star is not going to change if you had initialized at B star because V star and B star together already fit your data. And this is the square law, so there's no margin and all of that to think about. So if you're initialized perfectly, everything is good. But you're not initialized perfectly, you're doing random initialization. And so the quantity that matters here is how far your random head V naught, how close it is to V star. So the farther your phi is, the farther V naught is, the larger phi is, and your OOD error could be higher. So basically, because if V is a lot farther from V star, then B will also change a lot to accommodate this farther V while doing gradient updates. And so if you want to combine them or put them together in this, what we find is that for all steps in fine tuning, so for every T, we see that as you approach the perfect pre-training representation, the OOD error of linear probing versus OOD error of fine tuning approaches zero. So LP does much better than fine tuning as your pre-trained model goes towards the best pre-trained model. And under the conditions that the principal angle, this is B star here, between S and B star and between S star and B star is non-zero. So these are just making sure that you're not missing, there are directions that you are missing out. So as long as that happens, then you are in the situation that linear probing does much better than fine-tuning OOD. Whereas ID error, which is just measuring on the subspace for which you have training data, we can prove that fine-tuning always does better, even if B naught is far from B star, fine-tuning, especially when B naught is far from B star, fine-tuning does better. If both B naught is equal to B star, both perform the same, but fine-tuning is always better, never worse. And the tool about how we kind of obtain the result is basically to leverage some kind of invariant that shows how V and B are related throughout the process of fine tuning. So we have you can basically write out an equation for what V and B look like at every time step. And that basically shows that if V is very far, then your B will also end up changing a lot to keep that invariant. Whereas if V was close to V star, then your B won't change much because that invariant has to be preserved. So really crucial thing that comes up is that the way you initialize the linear head plays an important role through this invariance that is held in the process of fine tuning. And so this allows us to like not worry about exactly non-convex dynamics and stuff. And we just like, look at the invariance to get a sense of what V and B are. Maybe I'll skip this in the interest of time. So that's basically a similar intuition. And so to summarize, fine tuning has worse OD performance when the pre-trained features are good or this epsilon is small and the distribution shift is large. And this is what we saw in practice as well, where there are more missing directions in training data. And this occurs throughout the process of fine tuning. And so early stopping, like even more aggressive early stopping won't fix this problem. You will still like each time you make any update to the features, you can actually find that worst case, it's going to affect your OD performance because your head is randomly initialized. But within distribution, fine tuning is always better or equal. So now, hopefully this, I think some ideas are already coming up, but what kind of theory solution would this say? So how do we get the best of both worlds? So why does fine tuning do better in distribution? That's for the simple reason that your pre-trained features might not be perfect, so it may not be linearly separable. And so changing the features does give you more leverage to actually get good performance in distribution. So especially if you have imperfect pre-trained features, this is crucial. But why does it do worse out of distribution is because the features can change a lot to accommodate the randomly initialized linear head. And that's what came up in those invariants that we had for the gradient flow equation. But if we stare at these two things, like the natural thing to think about is we actually only need to change the features to fit your training data. We don't need to change the features to accommodate this head. So changing features is fine as long as you're changing it in a meaningful way. So can we refine these features without distorting them too much? And that would probably give us the best of both worlds. And so the idea here is that we first do linear probing. So we learn the best possible linear head that we could have without changing the features. And now now we might not fit the data perfectly because the features were not perfectly linearly separable. But now let's refine the features, but we'll do so with this linear head as initialization because we don't want to simply change the features to accommodate a random linear head. So what we do here is like we first do linear probing and then we refine the features. So the features separate out a little more to accommodate these, this linear head. So in the process, we have still kept the OD performance because the linear head hasn't changed much, but the features have changed a little bit. And so that enables you to get better margin and better performance in distribution as well. So that leads us to this Lpft method. I guess we didn't get a better name, is you first do linear probing and then do fine tuning. And so we can actually prove that linear probing, this method does better or dominates both linear probing and fine tuning, at least when the features are perfect. When the features are not perfect, it's a little more involved in like proving things. But in general, the idea is that this process enables us to make changes to the features that are only actually matter as opposed to features that change simply because they're accommodating the randomly initialized head. Yeah.
What do you mean by perfect?
Like if B naught is B star. So it's slightly trivial, but at least you can prove in that case. When B naught is not equal to B star, it becomes a little more involved for proving that it dominates both. Yeah.
It seems that the theory works when your outer distribution covers like more directions than the in distribution, right?
Not yeah, it has to at least a few unseen directions.
But it subsumes the.
Not necessarily. I mean, it doesn't have to subsume. Like even if it doesn't, like linear probing would do better if those directions are more like I mean, you pay more attention to unseen directions.
Right.
You'd have at least one or two unseen directions. For example, that itself would cause the gap.
Right, but I'm just going back to like the losses will only converge. The losses will only converge if your K was.
It just has to be non-zero.
Non-zero.
Yeah. Yeah. Okay, so like we can quickly test whether this holds in practice. And it's like, so these are the results from the same data sets as before. So if we look at Lpft, which is this kind of just a very small tweak to this process. So what we find is in distribution, we actually, in fact, do better, probably because even in distribution, like this is offering an additional regularization. And so that does preserve more of the pre-training information that helps in distribution as well. And it definitely helps out of distribution. And so, you can see that it obtains the best of both worlds. And this was kind of interesting because it's really a very small tweak to the process. And in fact, we found some blog posts that said that this works better or something. So this is definitely not like a very novel idea, but it's something that people weren't doing. And we find that just a small change to the way you fine tune can improve your in distribution and out of distribution performance. So get up to about like 10% over the vanilla fine tuning without compromising in distribution at all. Yeah.
Is the weights in the linear head changing at all during the second time?
It doesn't matter too much, but yes, we do change the head too. Yeah. But in practice, it changes by a very small amount. Even if, yeah. And so just to dive into the results a little bit more. So these are the in distribution accuracy. So it's not perfect. It's not always dominant. So this FMOW is like a data set which is we were only using mostly ImageNet pre-trained models, and FMOW is like slightly far from ImageNet pre-trained models. So the features are not that great. And so in this case, you actually see Lpft does worse than fine tuning. But on most other data sets, it does better. And out of distribution, it does better than other methods. Okay, so we also dug into this a little bit more, and we did see that the intuition that in distribution features change more than out of distribution features, at least in L2 distance, does happen when we do vanilla fine tuning. So it is true that there is some kind of distortion because of that. And when we do Lpft, we find that in distribution features now change an order of magnitude less than what they were changing when we did vanilla fine tuning. So just by fixing the linear head initially, we make the features change a lot less, even though we're running the same gradient procedure. Okay. So just to summarize this part, we find that pre-trained models give a large improvement in accuracy, which is kind of interesting, and we don't understand totally why yet. But also how we fine-tune or use these models is kind of key. And Lpft is just a starting point to even prove the proof of concept that there is stuff that we can do to get better than what we currently have. And in fact, in NLP, people have been exploring this kind of lightweight fine-tuning where you only change a few parameters or something like that. And again, people typically do that for saving computational costs, but even there, the similar idea holds, and we improve robustness for perhaps a similar reason that the features change less if fewer things are changing, and that helps. And in this whole discussion, we've assumed linear networks and 2 layers and all of that. And so maybe that only allows us to make a simple change, but perhaps we can get much more insight and much more advanced changes if we actually try to analyze what happens with nonlinearities and deeper networks. And yeah, so that might open up a broader set of adaptation procedures to actually think about what is the optimal adaptation procedure. And of course, like I said in the talk, there are several moving pieces when we think about this whole transfer learning or pre-training setting. In this talk, we only talked about adaptation procedure, but all of these questions and how especially pre-training and adaptation interact, and what is the right pre-training procedure? Someone asked, why does representation learning work, and what is the right objectives? And people have been coming up with new and new objectives empirically, but we don't have a good theoretical handle on any of them, and how all of these components interact together at the end of the day. These are all open questions, of course. And okay, so I have a few minutes. I'll maybe flash each slide. So with a couple of results in supervised learning that I'll maybe focus on observation so that people in the room here can actually figure out why and what's happening. So this is a pretty interesting observation we had in this paper, and we call this accuracy on the line. So what we find is that if you plot in distribution accuracy versus out of distribution accuracy, strangely across many different model architectures, they all lie on this same line with a particular transformation. So there is some very intriguing structure in both the distribution shift as well as how the models learn that causes this observation, where in distribution accuracy perfectly predicts out of distribution accuracy. like for example, if each model was doing something different, like we should have been able to see that they extrapolate out of distribution differently, right? But for some reason, there is something very universal about how all of these things use the data. And of course, the data distribution, the shift itself, that causes this observation, and we don't have any insights into this. And the related thing we found is that it doesn't just have to be accuracy. If we take a few models and look at how much they disagree with each other, we see that the disagreement also follows a similar trend. So if you look at how much models agree on one distribution versus another distribution shift, that also perfectly predicts what happens out of distribution. So this is practically useful because disagreement doesn't need labels. And so, it is useful from a robustness perspective, but it's also very interesting from an understanding case. I don't have the plot here, but it's in the paper. We find that this slope matches only for neural networks. So in the previous case, we had in the accuracy case, all different like SVMs and KNNs and all of that also lie on this particular line. But in this agreement case, we find that only neural networks disagree and they lie on the same accuracy line, whereas different models, they have different slopes. So somehow the neural network matches the accuracy slope, whereas for other models, they have different slopes. So that shows something more fundamental about why agreement between networks actually follows accuracy much stronger than other models, which we don't have any understanding about. I'll skip this. The other thing that I think which is quite interesting is this simplicity bias. And so if you try to understand, usually in theory, we assume linear features, Gaussians, and look at trying to prove things. And typically neural networks do the right thing, learn max margin and so on. But if we actually have a more nuanced setting where some features are more simple or complex than the other. So here is a synthetic data set we created. So we have MNIST, which is much simpler than CFAR. So we created a new input by concatenating the two. So the model, if you're trying to label this, it could either use MNIST to generate its to generate its prediction, or CFAR. And ideally a model would use both, right? Because both are predictive. But if you look at actually what happens, so if we randomize the CFAR part and look at the network's predictions, you see that the logits are almost identical. So we kept the same MNIST and replaced the CFAR 10 with some other part, some other class. The network's predictions are identical. So what this means is that the network completely ignored whatever CFAR 10's predictive component was and only looked at MNIST. And so if we randomize the MNIST, of course, we see that the logits change quite a bit. They actually reflect the fact that it's randomized completely. So this shows that both of these plots together basically show that the network completely ignored CFAR and only used the MNIST part. And this is a bit troubling for me because there are many predictive features in the data set. And of course, we want the model to at least use everything and not completely ignore some features. So we'd find that it's not really, in that sense, it's not the right max margin solution because you get much more signal and separation if you were using both. Right? So if we are in the setting where you have some linear, some nonlinear, or more complex features, we're actually not in the case that neural networks do kind of the right thing and learn the maximal separation. They actually tend to ignore certain features. And this is actually something we see repeatedly in robustness. For example, spurious correlations come up because of this. So if a model looking at the background is much easier than actually learning the features of the object. And so if you had very good correlation with just the background, then the models are going to use the background exclusively. And they have to completely change the training process to make them learn anything else. And again, we don't have a complete understanding of why this happens and what we can do to fix it, other than, of course, data augmentation. But that's not that interesting and not that general. So I think that's a pretty interesting open question. And with that, I want to thank, so there are a lot of other collaborators, but the work that I spoke the most is work with Ananya, Robbie, Tengyu, and Percy. And also want to thank Google and Open Philanthropy for supporting a lot of this work. Yeah, thanks.
Not that much time, and maybe just one question.
Yeah.
Thanks for this book. Just on the previous slide, the quick question was what class of labels you give to?
Oh, sorry. Yeah, so suppose, so this is class 0 and this is class 0. So we give the label 0. So both, yeah, so it's basically
So
like,
you just
yeah,
match.
you just match on both features. So both features would have given you 0 independently, but now we put them together and see what the network learns. And we find that, so the network could have learned CFAR if it had only CFAR, could have learned MNIST if it had only MNIST, but both put together it learns only MNIST.
And I guess the main, I feel that you could phrase that another way where it's actually good that it solves the problem in the simplest way it could. Or like
yeah, but the problem with that is in most real world cases, we don't like this, like we don't have a control on what things could be predictive or not. So like why this is bad is, say you're doing like calibration or like you're trying to use network confidence, right? So suppose your distribution shift happens or something happens and then now your CFAR has changed. The network should at least detect that some features that could have been useful are different. Now you can't even detect that because the network just completely assumes they're unimportant. So in a setting where those probably were the right features, this is quite problematic. Thank you.
We have a break now.